Okay, so today we're continuing to talk about growth and decay. Our last lesson, I just call an introduction to exponential growth and decay. I should say exponential growth and decay here, but it doesn't fit in the spacing for the aim, so it is something that is exponential. We use a base of E because in population growth or half-lives, when we're talking about decay, everything deals off of a natural base, E, Euler's number, so it is exponential. So I have here basically the same thing that we were talking about yesterday. So if you have this already into your notebooks, that's fine. I just want to discuss that a little tiny bit. So you're going to notice that you have the equation y equals ce to the kt, and like I said in the last lesson, please do not just plug into that formula if you know what c and k or t is and solve for c, etc. Do solve your differential equation to get it into that form. But what I want to bring into light is that k is positive if it is an exponential growth. And by saying that, you're probably thinking, well, if k is negative, well, if it's negative, then it's exponential decay. So please write that down. It's supposed to be A, Y. There you go. It's a little script. All right, so sometimes we have a differential equation, and it's in the form of what we call relative growth rate. Okay, particularly P is usually our population. So we have dP over dt is equal to K times P. All right, and this is what we're working with in yesterday's example, something like this. This is used to represent the population, and when we solve this differential equation, it should be in this form, okay? P is equal to P sub 0, so that's your initial population, e to the kt, where P sub 0 is the size of the population at the time t is equal to 0. Yes, I did get tongue-tied there. I'm sorry. Okay, so we are going to work a little bit more, talk a little bit more about this today, but there is something else that we do go over, and it's called Newton's law of cooling. Okay, and now as I usually say in almost all my videos, if you didn't get something down into your notebooks, please stop and rewind, pause the video, whatever, to get it down. Because now we're up to Newton's law of cooling, and you do actually need to know this formula here. So it's actually something you need to memorize. It's not like a derivative rule or anything like that you need to memorize, so it's an actual formula. And I'm sorry you have so much to memorize already. And there's just one more. And here we go. T minus T sub S, if you can see that, is equal to the quantity of T sub 0 minus T sub S times e to the negative kt. The reason why k is negative is because this Newton's law of cooling, okay? It can be applied to warming as well, as this is there. So T by itself is usually what we need to solve for. T sub 0 is the surrounding temperature, okay? Maybe it's a room, maybe it's an oven, especially if you're trying to warm something up. T sub 0 is the temperature when T is equal to 0, so like an initial temperature. Again, T sub S is the surrounding temperature. E is our base. It's a number, constant, about 2.718. K is also a constant, and T is time. All right? And All right, so believe it or not, I'm going to derive this for you. Now, you do not need to know, study, memorize the derivation, but it's something that I just wanted to show you so you can understand like what's going on here. So based on what we have for like a relative growth rate, or even when we've solved for the exponential growth and decay, dt over dt, so I have to emphasize d uppercase t over d lowercase t is equal to negative k, not times p, but times the quantity t minus t sub s. Okay, multiply both sides by our lowercase dt. And we're going to move over those capital T's, that quantity that we see over there. So, okay, so let me write out that next step. What I'm left with over here. So I can integrate both sides, and remember that k is a constant. I can keep it there. I can actually factor it out with the negative, and over here it lists a parenthesis. There actually is another constant. T sub s is a constant, okay? It's something we're going to plug in for the surrounding temperature. So when we're evaluating this integral and we need u substitution, then du is actually just dt. So this is what we end up with. And we're going to, I'm going to evaluate this. You know what? I'm going to use that as an arrow. Left side of the equation, ln absolute value of u equals negative kt plus c. That's a k. And then we're going to use e on both sides to get the absolute value of u is equal to ce to negative kt. Hopefully you remember what we did to get that c from previous lessons. Okay, e to the c times e to negative kt, and e to c is c. So we view that from previous lessons. I'm going to plug back the u value here. Again, that's a k that you see. And again, you don't have to show this derivation, okay? Unlike I said in previous problems, solve the differential equation. Here, we don't have to. Just plug into the formula if you know it. And T sub 0 gets plugged in at this point. So this is how it kind of comes about with your original temperature. By the way, first case scenario. I'm going to need more room. Okay, so if the temperature that we're looking for is T sub 0, that is for when T is equal to 0. This is helping us solve for C. Okay, so e to the 0 power, which is what you would get here, is the same as e to the first, which is 1. And you can see how C turns out to be this expression. So now let's put that back in where we see T in our original. So T minus T sub S is the quantity of T sub 0 minus T sub S, because that's what we just found to be C, times e to the negative KT. All right, so we just derived this. Again, you don't have to, just kind of memorize this formula. Now, I don't see it often on the AP exam, but I did come across one question with it, and I was like, oh, thank goodness I covered it. So you're going to use this for your practice problem and see how it goes. Let me know if you have any questions. And I'm going to give you a different type of example problem that has to deal with finding a proportion. Okay, so as you're copying this down, I just want to say one more thing about like the last slide. When it comes to problems that you would use Newton's law of cooling, like with a hard-boiled eggs being run under water to cool, or soup being cooled to room temperature, or maybe even heated up. Whatever the time is, you use that unit of measure. So if it's given as minutes or hours or whatever, you don't have to change it into seconds like your science classes, okay? Just keep the unit of measure that they give you. Speaking of keeping, so we're going to keep doing problems where we deal with an exponential growth like population, and we know that our population here for this region is increasing. You can see that in the table that's given. Now this table is really important actually. We want to know by how much is this increasing. This actually helps us find K. So there are some problems where we know that our population is growing by 3% like we had in the previous problem. So we knew what K was. But here, it's not telling us, hey, it's growing by 3%. So what we do is we try to figure out what a proportion might be, and we set it equal to e to the kt. Let me solve. So for this particular data, okay, if we take 502 million, but you don't need all the zeros, over 494, okay, that's between 2006 and 2007. What did it grow? We want a positive number. And we're getting about 1.0162. Okay, so I have 4 decimal places for my work there. And then I'm going to examine what it is, okay, going up by from 2007 to 2008. So we want to see what the overall picture is by the time we get to 2011 here. Okay, so it's some years ago. So as I do this, please make sure this is in your notebooks. This isn't too hard if you have a calculator. Okay. So take your time and take a look at the numbers that you're getting. Oop. Make sure you write down the right numbers. Oh, there we go. Okay, so if you take a look, okay, at all of these numbers, the first one being 1.016, the next 1.018, the next is also 1.018, the next is 1.025, okay, so that one, it grew pretty much higher than the other years. And then it's about 1.017. So, for the textbook or from the College Board, wherever I pulled this question from, they used 1.018. You can also use 1.017, and they would still give you credit, okay? So that's what we actually make equal to e to the k to find out what that k value is that we're working with before. Because if you remember about like the 1 plus whatever the increase is, that was based off of no natural population growth. But here we have to express we do have a natural base. Okay, this is an exponential growth that appears in nature. So that's what we set our proportion equal to. Okay, so when we solve this, K turns out to be approximately 0.0178. So once again, it's 4 decimal places because it's still part of our work. And that is what we're going to make dp over dt equal to 0.0178p. And then we just solve it like we have done in previous problems, okay? So let me do that quickly. Let me know if you have any questions. Just bring it to my attention, and I'll be happy to kind of help you out there. So here we go. Are you ready? I hope so. Multiply both sides by dt, and divide both sides by p. Integrate. ln absolute value of p is equal to 0.0178t, and both sides. We only need the positive for our absolute value. Ooh, don't forget the plus c. All right, I corrected that. And we got p equals ce to the 0.0178t. Okay, so now, make sure this is in your notes. I have to erase some space here so we can solve for C. It says find an initial value problem for the population and use it to predict the population year 2030. Okay, so if let's say T is equal to 0 represents 2006, okay, then T is equal to 24 for 2030. But we're going to use 0 and 494 or 494 million, okay? Either one is fine. I'm just using the 494 to make it easier for this problem. So you've seen problems where we used all the zeros. Now I'm just using that it would be in millions of people. Don't worry, it will be expressed very similar. So if P is equal to 494 and T is equal to 0, then obviously C is also 494. And we're using this to figure out the population. Okay, again, and this should be an equals, when T is equal to 24. So when T is equal to 24, this is obviously a problem for the calculator, then we get that P is approximately 757.282 million people. And that's how we don't need all the zeros. We just state it's in millions of people. Okay, I just want to clarify that number. Let me know if you have any questions. Let me know if you need help. And do the practice problem. Get your feet kind of wet with that Newton's law of cooling, because I think you should be good with this stuff. Good luck.